Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Yeah, welcome everyone. I'm very pleased to have the honor to introducing Irina Gurevych. And Irina is a professor in the Department of Computer Science at the Technical University of Darmstadt in Germany. And she is also an adjunct professor at the Mohammed bin Zayed University of Artificial Intelligence in Abu Dhabi, and an affiliated professor at the Institute for Computer Science, Artificial Intelligence and Technology in Sofia in Bulgaria. And Irina is widely recognized for her fundamental contributions to innovative applications of natural language processing and machine learning. And she's in the past also was the president and is now a fellow of the Association of Computational Linguistics, ACL, which is the leading professional society in the field of natural language processing. And furthermore, Irina is an ELLIS Fellow and the director of the ELLIS program Natural Language Processing, and she received an IRC Advanced Grant. And we are very much looking forward now to your presentation, Irina, on the topic towards real-world fact-checking with large language mode.
Great. Thank you very much, Konrad. I'm delighted to be here. I belong to the ELLIS NLP program. Just to remind you, ELLIS is the European Laboratory for Learning and Intelligent Systems. And this network is focused on scientific excellence, innovation, and societal impact.
Just briefly, Irina, sorry, you're not sharing your screen. I don't know whether you're meant to be sharing it already.
Yes.
Okay, thanks.
Let me check. Should be good now?
Perfect. Thank you, Irina.
So ELLIS has the objective to advance AI research in Europe to enable Europe to shape machine learning and AI of the future. And ELLIS NLP program was among the first established in October 2020. Together with my colleagues Ivan Titov and Andrei Martins, I'm the co-director of the ELLIS NLP program, which currently has about 20 members and a high number of additional participants taking part in our events. The ELLIS NLP program has the main focus on conducting scientific workshops on open challenges and future directions of natural language processing, where we share insights and discuss emerging topics, as well as a strategic roadmap for European collaborations. My topic today is about disinformation. Disinformation is a growing threat for our society. There are numerous examples how misinformation can affect our lives. For example, in the healthcare domain, people may die from taking the wrong medicine, as there were examples during the COVID-19 pandemic. On the other hand, we have a lot of image-based misinformation. where claims are related to images. Here in the example, Ukraine is building a dirty bomb, while the image stems from a different context and was actually taken at a nuclear plant in Russia. Fighting disinformation relates to the overall topic of this series, AI for social good. In particular, the main goal related to this topic is peace, justice, and strong institutions that need fact-checking to maintain trust and access to true information within our society. And in addition, this topic is related to other objectives such as good health and well-being. I have shown in my examples how this can be relevant to healthcare, and of course climate action, where a lot of public discourse happens around the topic and many claims are put forward that require attention. First of all, it's important to define what we mean by real-world misinformation. Misinformation is represented by non-true harmful claims that professional fact-checkers think important to verify, and it is characterized by two key properties. The first is the volume. So once a piece of misinformation enters the space, it is replicated by multiple users and gains a large volume. And also misinformation is relevant to many people. So people are interested about these claims, and therefore it is important to fact check them very quickly. Now, looking at some real life examples from common NLP data sets, we find claims like, for example, Coldplay is French. 500,000 sharks could be killed to make the COVID-19 vaccine, or Beat It is not a song by Michael Jackson. If we think about it, what is real-world misinformation here? So probably most people will point to the second example. 500,000 sharks could be killed to make the vaccine. So this example seems to be more complex, and also it is hinting at a fact rather than stating a direct fact. However, it turns out that two examples on the left side, Coldplay is French and Beat It is not a song by Michael Jackson, are actually from the mainstream NLP data sets for fact checking. And comparing this with the example on the right-hand side, we can ask a question: why is harmful real-world misinformation challenging? One of the main reasons for this is that while the facts Coldplay is French and Beat It is not a song by Michael Jackson could be verified by a single source, for example, by looking up some documents on the internet, it is much harder, if not impossible, to do for the statement 500,000 sharks could be killed to make the COVID-19 vaccine. It is much more nuanced, and it could require, for example, also mathematical reasoning in order to determine the number of animals that have to be killed, and also the exact ingredients of the vaccine and relations among the components of this claim. Now I'd like to give you a rough idea how mainstream fact-checking is working in natural language processing. Typically, we have a claim. For example, Sydney is the capital of Australia. And then we retrieve evidence from a trusted knowledge base. It can be a big collection of documents, for example, on the internet or proprietary knowledge base, or it can be also a database or a classical knowledge graph. So we would retrieve evidence related to the claim by using some similarity measures. And this way we have pieces of evidence or counter evidence for the claim. So for example, such a piece of information could be Canberra is the capital of Australia. And Next, we apply veracity prediction. So here we put these two statements into a textual classification algorithm, and we try to identify the relation, support or predict, support or refute between these two statements. And if the evidence contradicts the claim, we can conclude that the claim is false. While this is a mainstream pipeline in current NLP, it turns out it is hard to apply this pipeline to real-life misinformation. Why is it so? So if we have a claim, hydroxychloroquine cures COVID-19, which is an example of a realistic claim that we have extracted from a website for fact-checking, it turns out when this claim is published on the internet, it is impossible to find counter evidence for this claim. At the time when it is published, simply no contradicting evidence exists. And therefore, the common mainstream pipeline of fact-checking in NLP can perform well on our data sets retrospectively, but it completely fails in a real-life situation. If we look at the debunking as it is performed by human fact-checkers, it is a complex process, and this process cannot rely on counter evidence for the reasons I've just described. So what do they do? Usually, fact-checkers have some background knowledge, for example, about the entity which is making this claim. So here it's the Tea Party patriots, and the human fact-checker can retrieve, for example, some documents from this party that describe their intentions, and it can reveal, for example, the motivation of the party making the claim. Also, the human fact-checker can contact other people or representatives of the party to obtain more background knowledge if needed. And the human fact-checker would evaluate potential evidence supplied with the claim. So here it's an article from an established biomedical journal, and the fact-checker will establish that this article is written in 2005, where COVID-19 did not even exist. It is about a different virus and also in vitro experiments rather than experiments on humans. So the main takeaway here is that humans use the source of a claim in their verification process. It is at the very heart of it. And they are required by the guidelines to consult the sources provided by the claimant and include them in the verification process. So the question, how do you know that, is at the heart of verification. Similarly, context is needed to find and use evidence based on the source. So if we just compare the claim with the provided evidence on the study, we can conclude that technically the relation between these two pieces of information is neutral. So there is no stance such as attack or refute. Basically, this context on the surface is irrelevant to the claim, and therefore it cannot support this claim. Though the claim relies on this context in the social media when it is published. And what is important here is that the semantic similarity that natural language processing algorithms usually use in order to determine the relevant pieces of information to check the claim cannot give us this relation unsupported. So there's something else going here at the interface between the claim and the evidence. So to summarize the importance of the source, current fact-checking systems usually only look at the claim. However, we need to find some indications and some context in order to actually check the claim if counter evidence does not exist for this claim. So we need to look at the source of the claim, and if we look at the source, we suddenly see further points of attack. We can now attack the reasoning behind the claim. For example, there might be fallacies at the interface between the source and the claim, or we can attack the claim based on the underlying source because the source of the information may be non-credible, or because the source of the information may contain non-factual statements that themselves can be refuted. So in my talk today, I will focus on two types of misinformation with increased perceived credibility. The reason for this is that such misinformation is especially dangerous since we have, for example, a claim on social media that we have a cure for a particular disease, and it is supported by a scientific publication as shown in my example, which is quite credible. So a lot of users may not be able to read and understand the article at depth, and they may trust the claim because it is supported by what seems to be a very credible content. The other part of the talk will be about the visual content. And here we know that an image speaks better than 1,000 words. So people tend to believe images, and there is a rising number of such misinformation circulating in social networks. These types of content are highly misleading, and we need special debunking methods in order to debunk such misinformation. So in the first piece of work, I focus on our work on reconstructing the fallacies in misrepresented scientific publications, which is done together with my PhD student, Max Glockner, and faculty colleagues Yufang Hu and Preslav Nakov. So as I've already explained, we need to assess a claim based on its sources. The currently existing fact-checking techniques are not sufficient here because for this claim, we have discussed there is no counter evidence, at least at the time when the claim is published. And also existing techniques for automated fallacy detection will not help us because they are usually based on surface features, just classifying the statement itself. However, the statement is very short and there is not enough information in order to detect a fallacy without further context. So as a context, we have this scientific publication, which is cited together with the claim at the time when it is published on social network. And what we are going to do is we are going to develop a methodology how we can detect applied fallacies in evaluating the source related to the published claim to be verified. So what we propose in our work is to reconstruct the fallacious arguments. And in our work, we focus on misinformation claims that misrepresent credible scientific studies. So here, the reasoning must be flawed, and we try to recreate the fallacious argument via its premises. So in the first step, we extract and represent every claim based on some part of the study. So we call this accurate premise. So this is actually the premise which in reality is contained in the scientific article that is given. So here it's chloroquine-reduced infection of the coronavirus. And in the next step, there is some content in the scientific publication which communicates specific facts related to this accurate premise. So here, for example, we have two fallacy contexts. So the first is the study used cell cultures for the experiments, and the second is the study was conducted on SARS-CoV-1. So these are actually pieces of content that we do observe in this scientific publication. So the model must find the fallacious premises that are needed in order to support the claim based on the claim and the study content. We need the study content to know that the results were only observed in cell experiments. To make this claim, we need to apply premise 1. The results can be transferred to humans because the human body consists of cell structure. So this is a fallacy of composition, the first reasoning mistake. And also the study uses a different virus than the one causing COVID-19. So we again need a fallacious premise here, and it would be that SARS-CoV-1 and SARS-CoV-2 are both coronaviruses, and therefore they can be treated in the same way. Again, this is another instance of the false equivalence fallacy. So our goal is to basically reconstruct the fallacious arguments in order to support humans in making informed decisions about the truthfulness of the claim. Since this is a novel task, we proceed with creating a data set in order to support separate steps in this complex fact-checking process. So we start by extracting data from a real-life fact-checking website where we collect all links in 527 fact-checking articles. And second, we manually identify all cases in which scientific publication is misrepresented. So this is exactly the case which I used in an example where we have some false claim and a scientific article is linked to it as supporting evidence. And this way we find about 200 links to misrepresented scientific publications from 150 fact-checking articles. So for this data, we manually reconstruct the fallacious arguments guided by the fact-checking articles in the way I have demonstrated in my example, and we obtain 435 fallacious reasoning steps. And then we need to locate the context within the article. So these yellow fallacy context. So here we use an automated methods in order to retrieve relevant passages from the article and rank them, and we take the top 6 as the relevant fallacy contexts. And we consolidate the data set, resulting in 114 articles, about 700 passages, and 2.2 thousand labels, with a sufficient level of agreement using the Cohen's-Kappa statistic at 0.6. Now I would like to highlight a few results from this work. So first of all, we find that we could not link all paraphrased context to a passage in the article. So we can link around 70–80% of them, and the reasons include multi-hop reasoning. That is when, in order to reason about the claim, we need multiple pieces of information, while we assume that a single passage is sufficient in this work, which represents currently a limitation. And also, we have sometimes non-textual content, which we also do not consider, for example, images, in the scope of this particular work. Another problem that we have is the mismatch in scope. So in this situation, we have a claim like cloth masks do nothing to prevent the virus, and the scientific publication talks about health workers wearing cloth masks that were infected. However, it turns out that the article talks about quite different study comparing effectiveness of cloth masks and medical masks. And so we have a mismatch in scope, because the publication context, the study did not include a group that did not wear masks at all, was not originally communicated in the related study. So this is why it is not always possible to link the claim to passages within the scientific publication. So next, we need to locate a passage based on which the claim is based upon. So here we have these green accurate premises that we want to find in the publication passage. And second, we want to retrieve all content passages that indicate fallacious reasoning. These are yellow fallacy contexts, which I used in the introductory example. So we explore sentence transformers for retrieving these types of information. And we find that specialized fact-checking models give better performance here at 0.6 of precision at 1, which is still leaving a lot of room for improvement in this task. Now, for the second question, what content points to fallacies, we use mean average precision, because here we have multiple pieces of information, and we achieve results which again are relatively good, but could be significantly improved, with the best result represented by a specialized instruction tuned sentence transformer at 0.54 map score. Then we look at a simplified task variant where we predict the applied fallacy class when the fallacious premise is provided to the model. And here we use large language models, and we explore different prompt combinations that contain a definition of fallacy. So here, for example, fallacy of composition, a logical form describing this fallacy, or an example describing this fallacy. So based on these different prompting strategies, we compare an open weights large language model Llama and a commercial closed model GPT-4. And we find that both evaluated large language models perform relatively well on this quite simplified task when the model is provided with the fallacy context. And we find that the best performance is given when we use the logical form and the example of the fallacy as part of the prompt. Now we make the task harder, and the task is now to generate the fallacious premise with the large language model and then predict the applied fallacy class. So we give as input the claim, the fallacy content, and the accurate premise, and then we receive a ranked list of generated fallacious premises and the fallacy classes. And all of a sudden, we can see a significant drop in performance. While it used to be at 0.73 for GPT, now when the model needs to generate the fallacious context itself that is recognized and reason about the fallacy, the result drops to 0.3. We have a more relaxed evaluation where the question is claim debunked by at least one correct fallacy among the set that the model has generated from any of the fallacy contexts. And here GPT gives stronger performance at about 0.6 for this measure. Now, in the last experiment, I'd like to mention, as part of this study, we want to see if large language models can write a fact-checking article, and this way we can measure how much they have already memorized during their training. So what you see are the results where we prompt the large language model to write a fact-checking article about a claim which is misinformation, since in our data set we only have false claims per definition. And we can see that the results are quite strong. So for many of the claims, the model can recognize the veracity correctly and write the corresponding fact check. In another experiment, we now take true claims to see how the model can deal with the true claims for comparison. And here we can see that a significant number of true claims are now recognized as such. And it shows that the model has a tendency to know the veracity from its parametric knowledge already. So in the next experiment, we want to see how the model behaves if we are giving the model all the relevant evidence passages. And a surprising result here is that for the false claims, if we give the model relevant passages along with the claim, the results become worse. So a large number of false claims, if given evidence passages, would be predicted as correct while they are false. So it seems like similar to people who might be misled by the content in evaluating the claims and also in evaluating the reasoning behind the evidence and the claim, the large language models can be easily misled in this scenario. Now, to conclude, in this part of my talk, I've presented a novel formalism to combat real-world misinformation. We have proposed a novel benchmark to test critical reasoning abilities of large language models in a realistic scenario of real-life difficult claims. And we try to bridge the gap between automatic fact-checking and fallacy detection. And finally, we have found, interestingly, that evidence from the misrepresented publication biases the large language model to believe that a false claim is true. So now let me talk about the second part, the visual content. So this is based on joint work with my PhD student, Jonathan Tongler, and Marie-Francine Meuns from the University of Leuven. And what we try to do is predicting the original context of visual misinformation. So why are we interested in this question? A recent study by Google and fact-checking organizations has analyzed the current trends in misinformation. And this study reports that 80% of the claims nowadays go beyond text and include multimodal information. And in the first place, they are images. They are dominant in the current misinformation space, while, as we see in the next graph, the number of videos is rapidly rising. And this is explained by the popularity of video-based platforms like TikTok, where such misinformation may be posted. So motivated by the rise of misinformation going beyond text, we are now conducting research to counter visual misinformation with a focus on images in this talk and possible extensions to videos that we are working on right now. So here is an example of an image with the attached claim, China victims of coronavirus, that was circulating on the internet. In traditional fact-checking, the focus is on classifying the veracity of this combination of image caption and the image. And the goal is to determine if the claim is true or false. However, in fact-checking, the fact-checkers are interested in methods which can provide more evidence and context about images. So this task is called image contextualization, and rather than just saying that the claim is true or false, the objective here is to explain the context of this image. So who has taken the image, why the image was taken, and so on. And this image contextualization is an important component of the human fact-checking process. It is used to detect check-worthy images for human fact-checkers, to detect out-of-context images, to write more convincing debunking articles and also to engage in pre-bunking communication. So when an image is already published, but the false claims have not even appeared, so we can anticipate which claims could be attached to this image. So in fact-checking work, the human experts usually go through a list of questions. And in this work, we use one popular framework for image contextualization, which is called the 5 pillars. This framework has been introduced by a fact-checking organization called First Draft. The 5 pillars are the provenance, the source, the location, and the motivation. And each pillar is associated with a question that I will illustrate using the example image. So the first question is, was the image used before? And in checking this, the fact checker says, yes, it has been used before. And the second question, who is the source? The answer to this question after investigation is Reuters. Then the third question is, when was the image taken? And it turns out the date is in March 2014. Surprise, surprise, long ago before the corona virus happened. And then where was the image taken? And even greater surprise, it turns out that the image is taken in Germany actually, and not in China. And finally, the last question is about the motivation behind this image. And it turns out that the image was a report on an art project. So based on the answers to these 5 questions that the fact checker is collecting using their traditional methods, the fact checker can debunk this claim that the image has been taken in China to illustrate the coronavirus victims. So how do human fact checkers accomplish this task? They use various tools to retrieve evidence that will answer each of those 5 pillar questions. The most standard tools they use are reverse image search engines. They take an image as a query and they return web pages that used the same image. And it happens that reverse image search does not return any results. An alternative is to define a set of keywords that they would use to describe the image, and instead of entering the image into the search engine, they use the keywords to look for previous images related to the given one. And there are many more tools which are highly specialized for geolocation and chronolocation that the fact checkers have at their disposal. You can imagine that this entire process is very time and labor consuming. It is also expertise consuming because the fact checker needs to reason about the results. And so our goal in this work is to see to which extent we can automate the process. Again, since this is a new task, we need to define the problem and present a data set for this problem. To study the task of image contextualization, we create a data set called 5 pillars, and we collect more than 1.5 thousand images from 3 different fact-checking organizations that are part of the international fact-checking network. Then for this data set represents 3 types of visual misinformation, such as out-of-context images, manipulated images, and fake images. In the next step, for each image, we task GPT-4 to annotate the 5 pillar answers based on the fact-checking article. GPT-4 returns a structured file that contains the answers to each of the 5 pillar questions if they are available, and meta information about the image. We find that all pillars are represented in more than 70% of the articles. And also, 40% of all images have annotations even for all 5 questions at the same time. So these numbers show the importance of the framework in real world fact-checking practice. We then want to validate the results of GPT-4, and we recruit 3 human judges to check the quality of the results on a random sample of images. And we are very happy about the results because we find that 98% of GPT-4 annotations are found to be correct, and the rest are missing annotations, which are a smaller problem than wrong annotations. So none are incorrect. And here in this task, we have high level of inter-annotator agreement that says that the results are statistically sound. Now, the 5 pillars are well represented in the fact-checking articles. Each pillar appears as a label in 65% of images at least. And the pillars often appear even in combination. So as I mentioned, close to 40% of all images have all 5 annotated pillars. And we then look at spatial distances between real and claimed locations of images based on our annotation, and we find a high discrepancy between real and claimed locations. And the same happens for the temporal distance. The real date of the event is often up to 10 years before the actual event. And again, this emphasizes the importance of image contextualization rather than a classical fact check, giving us the veracity without the context. We divide the task of image contextualization in 2 major steps. The first is to define a retriever that will query the open web to find relevant evidence. And the second step is to generate answers for the 5 pillars questions. In our work, we implement a baseline which uses the Google reverse image search as our retriever, and it collects the textual content of the returned web pages. And the answers are then generated by using few-shot or zero-shot prompting with the GPT-4 vision model. Now, I'd like to summarize the results. So I summarize the results by comparing GPT-4 using only image, using only text, or using both image and text. And this analysis is done for our 5 questions. So the first is about the source. So here we can see that multimodal input is better, but the overall performance is quite low. Obviously, we have not enough information in our evidence. It's like looking for a needle in a haystack. So for the date, we have medium results with text evidence, and interestingly, adding an image to the input even harms performance. So next is looking at location, and here the results are much stronger, especially combining both modalities of image and text. And we also find a discrepancy between date and location. So while for location, image information adds to the result, for date, image information hurts the results. And the final question is about the motivation. And here we also have medium results and almost equal performance using image or text evidence. Now, in summary, our baseline can be developed in various directions. So in our retrieval, we use just one evidence retriever, and the recall could be further improved. We find evidence for 2 images out of 3. Then for source, we found that the results are relatively poor, different to human fact checkers. The large language model cannot rely on interviews and profiling tools. For the date, the results are medium. We can't reliably link images to time periods and world events. However, the results for location are quite promising. So we can identify the location depicted in the image with quite good results, and especially on the country level of granularity. And finally, also the results for motivation are quite promising because we can reconstruct captions of images quite accurately and fill details with web evidence. There are many directions for future work, like better retrievers, agent-based framework to include more tools, and also adding world knowledge to image contextualization. In summary, I have talked about
Hi, Conrad. Yeah, we seem to have lost her, despite the fact that I can see her in the Zoom. I'm not sure what's happened, but let's give her a minute to reconnect. I'll message her in the meantime.
Okay.
Hi, Irina. Welcome back.
Hi, I'm sorry. My computer has restarted itself.
Bad timing. Okay. I think you
Um,
only had one or two slides left.
Yes, I was just about to summarize the talk briefly. So I have introduced the task of automatic image contextualization and a new data set based on real-world fact-checking articles. A lot of future directions are possible, including also evidence retrievers. And we have a lot more experiments in the related publication. So my talk was about misinformation detection for content types with increased perceived credibility that are highly misleading and for which we need specialized debunking methods. And we found that in scientific publications, large language models have limited critical reasoning abilities when it comes to fallacious scientific arguments. And large language models tend to consider false claims as correct when they are based on misrepresented scientific publications. And for visual content, GPT-4 Vision shows promising performance at detecting visual misinformation. Open source models are lagging much behind in performance, and image contextualization is an important and challenging task with many opportunities for future research. Thank you very much for your attention.
Thank you, Irina. So we have a couple of questions from the audience. So the first is, how does the talk relate to the Sustainable Development Goals?
Misinformation is at the core of the democratic societies of peace and justice in our society. So we are surrounded by a lot of conflicts nowadays, and here giving the citizens better tools in order to evaluate the information is quite critical. Beyond the political context, of course, the healthcare is a very important domain. There is statistics that a lot of people they actually die from taking wrong medicine based on some discussions in social media. And here again, we can provide critical tools in order to prevent this from happening. And finally, I have mentioned that climate is another important application domain where a lot of claims are made, but it's very hard to identify their veracity and related evidence. And here, misinformation detection can really make a big difference.
Okay, thank you. And then another question was, could agentic approaches be used for fact-checking?
I think this is very, very promising. We have produced just initial experiments and foundational data sets to study the problem. However, given the current speed of development in generative AI and also agentic-based systems, I think that they can provide more specialized tools that can evaluate information at a higher level of granularity rather than using a monolithic large language models, since they can also include much more specialized tools for specific steps of the process. So I think there is a huge potential in this area.
Okay. Very nice. And a third question consists of two sub-questions. What about contamination during the large language model training? And can it be the case that LLMs have seen the fact check and just cite the answers from their memory?
Well, this is indeed very, very tricky. We have shown some experiments where large language models can obviously write fact-checking articles based on their memorization and parametric knowledge. However, on the other hand, the large language models have not only seen the fact-checking data, but also the data where the claim is used as a false claim, right? So because of this, actually, the training data has seen both positive and negative instances, and the large language model still needs to identify if the claim is true or not, and also why it is so providing a rationale. So I think that contamination is indeed one confounding variable, and in future research, maybe we need to create some benchmarks, including claims that are recent and have not been in the training data. But the current results are also very interesting and relevant in their own right.
Okay. Wonderful. So we are in time very much. Thank you again for presenting today.
Thank you very much. It was my great pleasure to talk to you today.
Thank you.
Bye-bye.
Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.